garbage. I can't believe
Just like the World War II airplanes, with the badges, how they slowly shoot down. You can have little badges like little stars. Okay, I caught 5 of Texas yesterday.
So do we give you a grade?
I'd love a teacher that gave extra points if you caught his mistakes. I think that'd be a good idea.
All right. Well, I think the recorder is on already. Let me just double check. Yep, it is recording. And it has been recording for about a minute already. All right, let's go ahead and get started then. All right, let's go ahead and get started. Okay, I know this is a big class and it's a little bit harder to get focused. So let's go ahead and get started. Are there any questions about the homework assignment? Okay, so let's go ahead and get started. Are there any questions about the homework assignment? No, nothing about the homework assignment? Okay. Yep, go ahead.
So yeah, do I have to mess with the power server at all if I have to know what it's called?
You should not have to. Yeah, you can just use the virtual machine to work on it.
Because I'm saying if I don't have to use it, because I set up Linux on my computer, and so if I don't, do I not have to use the virtual machine at all if I have it?
Oh, if you, the only requirement is it has to work in Linux, and then the path of your folder or the archive file has to match the requirement that I'm looking for.
Okay.
Okay, so you can run, if you can run that tar command and it works, and then your last name is a part of that path, then you should be good.
Okay. Cool.
So what we'll do today is we'll go ahead and finish up the NDNS and instruction with discussion, which is something that we started on last Thursday. Okay, this is also something that you need for your homework assignment, and that's why I covered this material already. It's really just going through the slide to make sure that I did not miss anything that is important. Okay. So with this part here, when we specify the instruction, which is this one here, can someone tell me what is the mode or the accuracy mode of the second operand label 1? So far we have talked about 3 different types of operands. The first one is immediate, the second type is register, and the third one is direct. So can someone tell me what is the second operand in this case?
Direct.
It's a direct operand because it does not start with a dollar sign, it does not start with a percent sign, and it's not parentheses either. So this is a direct operand. So with a direct operand, what does it do exactly? Assuming label is really just a label. In other words, it's a symbolic name representing some kind of integer value. So what is it actually doing in this case? Okay. Well, the first operand is $23. What type of operand is that? It's an immediate operand. An immediate operand can only serve as source or destination. Source. As a source operand. So we are copying the value of 23 to somewhere. Now remember, 23, the value that we are copying, is actually a part of the instruction itself. Okay? So it is within the bit pattern of the instruction that we have that 23 in decimal embedded. Label 1, on the other hand, is also an integer. Okay? It is just the symbolic name of some integer. You can define it yourself. You can say, okay, I want to define label 1 to be 45. It's okay to do that. Whether the instruction will run correctly or not is a whole different question. Okay, but label 1 is basically an integer value. Okay, it's a 32-bit integer value when we're in 32-bit mode. So the question now is, what are we doing with this integer, the second integer in this instruction? It is treated as an address. Okay, so we are treating the integer represented by label 1 as an address. So the job of this loop instruction, which is a copy instruction, is not to change label 1 itself to 23. Its job is to go to the location indicated by label 1 and change that location to 23. Are we doing okay so far? In other words, this instruction accesses memory. It changes memory the value of memory locations. But how wide is the operation? How many bytes am I copying in this case?
4 bytes.
The default is 4. Okay, if I do not specify the width, then it will, it will use 4 bytes. It's the same as a move L instruction. Now, as a move L instruction, we have other questions that we have to ask. Because now that we know what is the width of the operation, because it is implied to be 32-bit, the question now is, what is the endianness? In other words, I'm copying 23, which is represented as 32-bit number. This is how 23 looks like. 23 in decimal. Okay. Can you guys kind of easily convert this to 23? How do you read this stuff here and turn it into the decimal value of 23?
1 plus 4 plus 16.
Plus 16. Yeah. So we have 7 plus 16, which is 23. Okay. So what are we going to do with this? Okay. This does not use up a single byte, and yet memory locations are byte addressable. That is the problem. Okay. That's why we have endianness, because each location is only storing a single byte. But occasionally, most of the time these days, we want to store multiple bytes, okay, or values that require multiple bytes to store. And the result, the question is, within these 4 bytes, how am I going to store these 4 bytes into 4 memory locations? In which order am I going to store everything? The little endian convention is basically saying the least significant byte has the lowest address. So that means within these 4 bytes, this one is going to the location label 1. This is going to the location label 1 plus 1. This is going to the location label 1 plus 2, and label 1 plus 3. When I say plus 1, 2, or 3, I'm adding individual byte locations. It is no longer typed. Okay? Remember, I kind of talked about how you really should forget about types in this class. Okay, when you're programming, you have to forget about types. When you use GDB, you have to kind of work around types. Because GDB still makes assumptions about types, and sometimes it gets in the way. And that's why I sent you guys the email, the forum, item to tell you, how to use GDB to go to a particular location. Because if you just say label 1 plus 1 in GDB, it would actually go to the location that is 4 bytes from location label 1, because it has an implicit type of integer. Are we still doing okay so far with all this? Okay. So the rest of this, really is just making this more better explained. Now, endianness little endian refers to the Intel method, which is summarized as least significant byte at the lowest address. Big endian is the opposite way, which means the most significant byte is at the lowest address. There's really no advantage, no distinct advantage to one or the other approach. They're about the same. So certain operations, big endian is better, but for other operations, little endian is better. So I would say it's basically a draw. There's no distinct advantage of this one is better than the other one. It's just a random choice for the most part. As I said, in the previous class, TCP/IP itself is big endian. Okay, if you have to transmit anything that's more than a bit, the most significant byte is transmitted first in TCP/IP. Right. So the test here is to give you 3 ways to express exactly the same allocation of 4 bytes and having those 4 bytes initialized to exactly the same content. The first one is treating these 4 bytes as a single 32-bit integer. Now, when we read a 32-bit integer, we are reading from most significant digit to least significant digit. So that means A8 is representing the most significant byte, 5.2 is representing the second most significant byte, D9 is representing the second least significant byte, and B2 is the least significant byte. The next one is using dot byte to initialize memory location. The same 4 bytes in the same order will be initialized using the dot byte directed here. But you can see the order is different because in using little endian, the least significant byte has the least address. So in this case, E2, because it is at the left-hand side of this line, it is the one with the lowest address. And then D9 is the next one. I missed the comma. Okay, good. So there's a syntax error here. 0x52 is the next one, and then the most significant byte is the A8. So this one may not be as confusing as the last one. The last one is really the most confusing one because it seems like the bytes are now crisscrossing, but it's really not crisscrossing. It looks like this because within the D9 B2, the B2 is the least significant byte. So we are still having B2 as the first byte within those 4 bytes. D9 is the second one. And then when we look at the second dot word, or the second word, which is a 16-bit 52 is the next one, and then 88 is the last one. So we are still defining the same sequence of bytes, even though it looks kind of weird and kind of crisscross all the way. Do we have any questions about this slide? So this is really the test of how well you understand the concept. Is can you look at these 3 lines of code and with the extra comma on the second one, and understand that they are actually defining the same 4 bytes in the same sequence. Are there any questions about this slide? No questions about this slide? Okay. If there are no questions about this slide, then we're going to move forward and keep talking about addressing modes. In other words, how can we have an instruction to get the content of a particular memory location? The only 2 operands that do not access memory, we have talked about those 2 already. Immediate does not access memory because it is embedded as a part of the instruction itself. Register does not access memory because registers are not a part of your memory. So those 2 addressing modes are the only 2 that do not access the memory. Every single other one accesses memory. Are we still doing okay so far with that concept? Now, depending on how you want to look at this, we can go through these slides in the same order as they are presented, or we can start with the last one, and then we turn our way, we go backwards, and then we, that way we can also explain, how the other addressing modes work. Okay? So it depends on how you guys want to look at it. It depends on how you learn. The last one is the most general addressing mode. It can do everything that all the other ones can do. In other words, you can look at 5.3, 5.5, 5.6, 5.7, 5.8, and 5.9 as special cases of 5.10. 5.10 is the most general way of addressing them. So do you want to go for the most general first and then move our way back and make it more specific? Or do you want to work with the more specific ones and then generalize as we proceed? So from general to more specific? Well, we can try that approach first. Okay, if it doesn't work, it will flip the order and go in the opposite direction. Okay. So let's start with the last one. Let's start with 5.10 here. And today I have to keep moving because there's a mosquito somewhere in the classroom, and mosquitoes like me. Okay, I don't like them, but they like me. I'm like, Twinkies to mosquitoes, with cream filling. So I don't particularly like that.
Did you say you were like Twinkies?
Sorry?
Did you say you were like
Yeah, to mosquitoes. Yeah. What's the cream filling, right? Yep, there, it's here. I have, okay, let me tell you something. I know this is a complete digression, has nothing to do with assembly language programming, but since we're talking about this, right? Most people have a triglyceride level of 200 or less. Okay, 200 is considered borderline high. Mine is last time. No, I shouldn't say last time. Last time it was okay, but before last time, before last time, it was 900 and something. And triglyceride is a kind of fatty thing in your blood. It's not cholesterol either, but it is a energy carrying kind of compound in your bloodstream, and mine is like all just way out there, 5 times the normal amount. And I think that's why mosquitoes like me. It's like, if a normal person is like, grape juice, mine is more like milkshake. It's like, oh, I need a thicker straw. All right. So we'll start with the last one, which is based, scaled, indexed addressing mode. This stuff works, okay? This is an explanation. But what I'll do instead of just reading my own notes is to explain it using mousepad. So if you guys see a mosquito landing on me, let me know, okay? I'll give you guys rubber bands so you can shoot it too, while it is on me. Yeah, I would much rather deal with the rubber band stain than having to deal with the itch from mosquito bite. Okay, so here is the general format of this, really generalized, addressing mode. It starts with a D. Okay, these are all tokens. In other words, it doesn't really start with a letter D. It starts with a number, but I'm just using D to represent the value of that number. So it starts with a D, and then we have what we call a base register, followed by an index register, followed by a scale. Okay, so in this particular operand has 4 components. D for the displacement or offset, you can use one or the other word. B for base register, I for index register, and S for scale. So I'll just go ahead and explain each one and what you can use for each component. D is displacement. It is an integer. That's all that it is. Okay, it's just an integer value. B is it's called the base register, but it is one of the registers that you can use. Okay, so it can be any one of the registers. So EAX, blah, 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 all the way to EBP, ESP, and so on. Those are all registers. I is called the index register. Can also be any one of the registers. In fact, if you want to, you can make the base register the same thing as your index register. There's no rule saying that they cannot be the same. So they can be the same even though the need of those two being the same is very few, if any. Are we still doing okay so far? What is the value of the displacement? It's the number itself. The value of a register will be the content of the register at the time when that instruction runs. Okay? So that part can change. And then the last part is what we call the scale. The scale is specifies. S specifies is the scale. It specifies one of the following numbers. 1, 2, 4, and I think 8 is also one of them. I cannot be 100% sure, but I think it is. Okay, because it only makes sense that there are 4 options and not 3. Because it's using 2 bits out of the instruction to specify the scale. So it makes sense that they will try their best to make use of all 4 possible combinations. Okay, so now that we know E is just a number, but that number cannot change in runtime. Okay, E is a number that has to be determined by assemble time or link time. So let me just make it very clear here. Determined by link time. And sometimes it is also determined by assemble time. So it's definitely before the program runs. By the time the program runs, the displacement is a fixed number. It's almost like an immediate operand. It is fixed. It cannot change anymore. B is a register. The value of a register definitely depends on the runtime environment. So the same instruction can have a different value depending on which iteration of the loop you're running. Same thing with I. The scale cannot be changed. Okay, so by the time you assemble the program, the scale has to be determined. It can only be 1, 2, 4, or 8. So let me also make it very clear. It is determined by assemble time. Okay. It is a number determined by assemble time. It specifies one of the following numbers: 1, 2, 4, or 8. So let me introduce another concept now. Okay, the effective address, abbreviated to EA, is computed as follows. EA in this case equals D, which is just a number, plus the value of in the register B plus the product of whatever value is in the index register times the scale. So D plus B plus I times S is the effective address, or the EA, of this particular operand. And I'll just put in extra parentheses just in case, someone wants to ask. Why do I have? Because I'm not 100% sure. I have not used a scale of 8, so I am not 100% sure that it is usable.
Could the base and the index be 16 and 8-bit, not just the 32-bit?
They can only be 32-bit registers.
They can only be
32-bit. Yep.
So the displacement can be either a symbol or link time, but the scale can only be a symbol time.
Correct.
Link time. Okay.
Yep. In other words, it cannot be a label. It has to be spelled out as 1, 2, 4, or 8
Right.
when you specify the instruction. All right. Are there any questions at this point? No questions? Okay. So the operand that requires or specifies all 4 components has that really long name. It's called the based scaled indexed addressing mode. Okay? And that requires all 4 components. Are there any questions at this point? But what exactly is an EA? What exactly is an effective address? Okay, so let me just explain that here. The effective address specifies at which location a value is either read or written to. Is read from or written to. Haven't we encountered one operand that already specifies a location to read from or written to? At this point, not even this instruction, before we talk about this instruction. In your homework assignment, we are already using one operand, one type of operand with one type of addressing mode that specifies a memory location. What is that? What was that again? The direct operand. Okay. The direct operand is actually a special case of this because we can look at the direct operand as the one as a specialization of this one without a base register, without an index register, and without a scale, with only the D component. In other words, the integer that you specify as the direct operand is really specifying the effective address directly, and that's why it's called a direct operand. Are we still doing okay so far? More or less. Okay. So let me give you, an example here. Okay. So if D is 465, if register, if B is %EAX and EAX has a value of, I'm just going to give it I'm just giving it a particular value here. Okay. Let's say index I is EBX and EBX has a value of, let's say, just 4. Let's make it 3. And the scale is 4. Then we want to look at the following instruction and say, okay, but where are we storing this particular byte? Then move B, which is a move byte instruction, and we'll specify the first operand to be just an immediate operand, and it doesn't matter. I'll just specify 57 as a number that I'm trying to store as the first operand, and the second operand is my the most general addressing mode that we can use in the Intel architecture. So this way, this time I specify 465 as my displacement, and then in parentheses I specify the other 3 components. The first one is my base register, which is EAX. The second one is the index register, which is EBX, and the last one is the scale, which is 4. Now remember, these are all just random examples that I chose for this particular illustration. So EAX can be any register, EBX can be any register. The displacement can be any integer value that is resolved by link time, and then 4 can be 1, 2, 4, or 8. You just have to choose one of those number. Okay. So what do you think is going to get the value of 57? Where am I storing the value of 57? That is the question. Is everybody comfortable with C operators, like dereferencing operator, typecasting, that sort of thing? Is that okay with you guys? Okay. So what I'm going to do is I'll give you the equivalent C code for this specific instruction. Okay? So I'll give you that code first, and then if you have questions, then I'll answer those questions. Okay. So the first thing I want to do is I'm going to typecast, the following thing as an address, as the address of a single char, because a char is a byte. Okay, and we are using a move byte instruction here, and that's why I want to make sure that I'm only going to copy to one single byte location. In the other parentheses, I'm just going to do the calculation. In fact, what I'll do is I'm going to copy the template of the equation and just put it here. And then I'll just go ahead and change D to the number 465. I will change B to the content or the value of the base register at the time when this instruction runs, which in this case has the assumption of 800,000. That's it, in hexadecimal. I refers to the value of the index register, which I assume to be 3 at the time when this instruction runs, and the scale is 4. That's how I specify the instruction. And of course, that is really just specifying the address. In other words, if you look at this entire expression, it is only specifying a number, right? It is 465 plus in hexadecimal 800,000, and the product of 12. I'm adding all of those numbers together, which is just a number. It's an integer. The question is, what am I using that integer for? Well, what I'm going to do is I'm passing that integer into a char pointer first, and then what I'll do is I will dereference that particular pointer with an extra dereference operator out here, and then I say this will get the value of 57. That's the C code corresponding to that one single instruction. Is that okay? Because I'm trying to map something that you are learning, which is the addressing mode that we're dealing with here, to something that you already understand, which is the C operator. In this case, it's just passing something into a char pointer first, so I can dereference that location and store something to that location. Is that okay? Is everybody comfortable with this approach? This is the first time I tried this. Okay, so I'm just testing to see whether you guys are receptive to this way of explaining the addressing. Is that okay? Any questions? Any questions about the C code? Because that really is the bottom line. If you understand the C code, then you can identify the various components in the assembly code and say, oh, okay, so that means this component goes here, this component goes here, and the whole thing is trying to specify the address in memory and store something to that location.
So if you were to convert the hexadecimal and then do the math, and then reconvert it back to hexadecimal, is that the address?
That becomes the address. Yep, absolutely. What does it turn out to be?
1 second.
I can probably do it with my.
It's 16 to the or 16 to the.
It boils down to a single integer value. Basically, that's what it is. Okay, I can try to use my command line calculator to do the same thing. Okay, so it's 8 times, there are 16 times 16 times 16 times 16 times 16, because there are 5 zeros in the hexadecimal number, plus 12, which is 3 times 4 plus 465. So the number turns out to be, in decimal, 8389085. So I'm going to copy that and paste it here. So the whole thing boils down to this operation. Yep.
So is the reason you're casting it to a character pointer because you want to copy an 8-bit representation of 57?
Yes.
Okay.
Because if I do not cast it to a char pointer, then it is a untyped pointer. You cannot store to a void, you cannot dereference a void pointer. So I cannot use a void. But I cannot dereference just an integer either because it doesn't know, the compiler would not know, okay, should I treat 57 as an 8-bit number, 16-bit, or 30-bit, or even 64-bit number? So I have to make sure that I cast it to the right width first before I perform the assignment operation.
GCC no cast as char.
Take it.
GCC no cast void pointer as char.
That's it. That sounds really dangerous to me. Because the whole point of a void pointer is we don't know what it is, and so it cannot be dereferenced. So if C allows you to dereference just a void pointer, it kind of defeats the whole purpose of having a void pointer.
Reference, but just make arithmetic operation.
Oh, you mean when you do the arithmetics?
Yeah.
Yeah. Mm-hmm. But in this case, the arithmetics are just integers too, so it's not even typed in. When we are talking about 465 is just an integer. At that time, it doesn't have the type of an address of something. So that's why I don't need to do any type casting when we're doing the calculation itself. All right. So is that okay so far? This explanation. Okay. All right. So now that we have this explanation, we can go back and talk about the other, the special cases of these components. So this is called the based, indexed, scaled addressing mode. We know this one already, right? If you only have a component of D, it is called the direct operand. When you have just this part here, okay, I'm just going to make everything line up well too. So if you only specify the base register without any other thing, it is called the indirect operand. When you specify potentially a D component and a B, there's a name for this one. It's called based addressing mode. And then you have D. You can specify nothing for the first one and only specify an I register or the index register and also a scale. So this one is called the indexed scaled addressing mode. Do you see the pattern here? I can choose, only a part of the most general form and turn that into what we call, it's just a specialized version of the, addressing mode. Okay. And, it keeps going like that. If you only specify the index register but without anything else, it is actually valid. You can do that if you want to. It's just called the index addressing mode in this case. Now you can see some of these are kind of utterly pointless, right? I mean, there's why do we want to use the indexed addressing mode where the scale is implied to be 1 when we can just use the based addressing mode, which will do exactly the same thing. Okay, so there's a lot of duplication here. And then we have the DBI, which is called the based indexed addressing mode without the scale. And if the scale is not specified, it is assumed to be 1. Okay. Any other questions about these other addressing modes? No questions? Okay. Do you think we need all of these addressing modes? No, we don't need all of these. How many do you think is actually required in order to simulate all the other ones? Assuming we have add instructions. Okay, so if you have an add instruction, you can perform addition. You can add a register to a register. You can add a immediate operand to a register, and so on and so forth. So how many operands are actually required in that case? We'll need register, okay? We'll need immediate and indirect. That's all that we need. Okay? Because indirect is the one thing that we need in order so that we can do all the calculations, store the result in the register, and then use the use the indirect operand to get to the memory location. Everything else can be emulated using one of those, a combination of those instructions. We'll talk about that later, but at this point we just want to kind of get familiarized with all of this stuff here. Any questions about the addressing modes? Now I can also point out which ones are really useful and when they will be useful in this semester. At this point, because we are not using anything on the stack, the direct operand is basically all we're going to use for memory operands. Okay? Yeah. That's all we're going to use at this point. When we are starting to use the stack for local variables, parameters, and so on, then this operand will become useful. The base operand is going to become very useful when we get to the stack, the call frame, and those concepts. An addressing mode is addressing mode applies to operands. So when you talk about an operand, you can say, okay, but what is the address? If it's a memory operand, then you can talk about the addressing mode, which is how do we calculate the effective address. So an addressing mode basically is just a way to specify how are we calculating the effective address of a memory location where we'll actually get content or store the content. Any other questions about this slide or what we have on the projector at this point? Yep.
So by default is DS data segment, and it also can be stack segment.
DS?
Yeah.
Without the index register? What do you mean by? Okay, repeat your question, please.
You need to address what segment, data segment or stack segment?
Oh,
and by
in this
default
class,
is DS.
yes. Okay, in this class we don't deal with the segment.
Okay.
So everything is just using one of these operands, and we do not specify the segment register, which is a very archaic concept.
But by default is DS.
By default, it is the DS. It's DS for the data segment, and then it's the code in the code segment is the SS is the. I can't remember what the S stands for, but it's the code. I think it's the CS for code segment. But those are all implied that we're not going to specify those registers in our operands. The whole concept of a segment register came about. Okay, this is kind of historical, but some of you may want to know why we have segment registers. The 8085 processor has a 16-bit address bus. So when we specify an address, we can only specify 1 out of 64 kilobytes of addresses. Okay, so you can imagine, with 16-bit address, you can specify, locations from 0 all the way up to 2 to the power of 16 minus 1, which is 65,535. Okay, so that's the value. And this is with the predecessor of the 8086 or 8088 processor. The Z80 is like this. The 8085 processor, I believe, is like that as well, with a 16-bit address. So at some point, people realized that 64 kilobytes of memory is not really enough for the operating system and also the application that they want to use. Okay? So what do? Well, there's no quick and easy way to extend the address, so they basically integrate the concept of a segment register. So what a segment register does is adding something to turn this into a 32-bit address. Okay? So you specify the same thing as a 16-bit address using the old addressing mode, just exactly the same way as before. But then there's what we call a segment register. And with a segment register, it is implied with certain instructions that a particular segment register will be used. A segment register by itself is also a 16-bit register, but the way they do it is they pad 4 zeros as the least significant bits, and then they add this segment register basically left shifted 4 times with an address to get to a 20-bit address. And that's the quick and easy and dirty way to extend a 16-bit architecture to deal with a 20-bit address bus, so that you can now have more memory to play with. effectively you have 64 kilobytes of address space without having to do anything to the segment register. Okay. I would consider that a hack to get to more memory space. And you can probably imagine that this mechanism still exists in the modern day i5, i7 processors because it is binary backward compatible. All right. Any other questions? So in this class, we don't worry about the segment register because we just say, okay, we calculate the 32-bit address, and that's it. Any other questions at this point? If there are no questions, we will go ahead and take a look at some examples. Okay, so we'll do some actual coding and take a look at some of these examples. So we go to cisp310, and we'll go ahead and take a look at some. Well, first of all, we'll take a look at the direct operand, which is something that we already know. Okay, so we'll take a look at the direct operand and start the code like this. We want to specify, we want to use the text portion of the text segment, or the text section, which is where we store instructions. So .text to start with the whole thing. .global underscore start. Remember what that does? It exports the label underscore start so that the linker has visibility of this label. And then we say underscore start colon, which is the definition of the label underscore start. It's basically saying, okay, the first instruction of this entire program is at the label underscore start. Yep.
Is underscore start like a main function?
Yes, underscore start, basically serves the same purpose as main in a C program. Yep. It's the entry point of everything. Okay. So what we'll do is we're gonna, say, okay, move word. Okay, I'm just randomly choosing a width here. Moving 16-bit, and then I can specify. Well, I'll make this a little bit more tricky. I'm going to specify the number to move or the value to move as a number that. Okay, it's 47 in hexadecimal. Okay, and I will store that to a location, and to make a certain location here that can actually store something. I'm going to use .data here to basically say switch to the data segment or the data section so that we can allocate space that can be overwritten. We'll use L1 colon to define label label L1. And then we'll go ahead and allocate just 1 byte. So we say .byte, and I want to initialize that location with a particular content. Let's say we want to initialize that content with F3 as the content in hexadecimal. So I would use a direct operand to say, okay, overwrite the location at L1 and change that to hexadecimal 47. Are we doing okay so far with this instruction? Okay. So this is a fairly simple example, and then we have the exit code. The exit code is not really needed because I'm not going to get to that part in GDB, but just as good practice, I'm going to specify that. All right. So here's my first program is using just a direct operand, and I think we should not be. We should know the result already. Okay, it's just going to copy, overwrite the content at L1, change it from F3 to 47 in hexadecimal. So we'll go ahead and double check, make sure that this program runs and it runs the way we think it should run. Assemble, and then we do the link. Oops, forgot the extension here. And then we can link it. LD-O direct.O GDB direct. Go. List. Put a breakpoint on the first line of the instructions on line 6. And I already have a problem here. Okay, can anyone point out what is the problem with this particular program? It's not exactly a problem. It is going to run, but if you look at the way I initialize, allocate and initialize memory, it is not really consistent with the way I utilize the memory locations. What is the problem here?
moving a word onto a byte?
Essentially, yes. Okay, but the instruction is going to be okay. If you look at line 2 is only allocating 1 byte and initializing that location with the content of F3. Does it say anything about the byte after that? Whether it should be allocated or not, or how I want to initialize that location? No, not a single thing, right? It's just that I know when it allocates memory location, it cannot allocate just 1 byte. So I know the next location is going to be allocated anyway, okay? And it's going to be initialized to a 0, okay? But it is not good programming practice to do something like this.
So is this called like alignment?
It doesn't do we don't need to enforce alignment.
Okay.
Yeah, you can actually do anything at any byte order or the byte boundary. It will work just as well. It's just going to be a little bit slower. That's all. Okay. But we can still kind of find out what this instruction is going to do. So we'll go ahead and run the program. The first thing we want to do is to locate or is to print the actual byte at location L1. The way to do this is we use the X command. I think most of you should already know how to use the X instruct or the X command inside GDB, because in order to do your homework assignment, if you don't do it on paper, you will probably have to use the X command to help you understand how memory is laid out. So in this case, I use the X command to look at memory location at L1, and sure enough, it has a content of F3. When you look at this number here, this part here, that is the actual address of that location. Okay, so in other words, L1 is this value. L1 has the actual value of, in this case, 8049089.
Can you print the DS segment?
Print the DS, the data segment? Okay, so IREDS, just IR. The data segment, is that a data segment? 7B? Doesn't seem to make a whole lot of sense, does it? Okay, so getting back to our program, let me go back and list the program again. All right, so we are about to execute line 6, okay, the instruction on line 6. So I perform a single step, and then I use the X command again to take a look at the location, and sure enough, it is now changed to 47. So the program works the way it is supposed to, okay, no problem. Even though I'm not supposed to overwrite a single byte with 2 bytes. Did the assembler complain about this?
No.
Did the linker complain about it?
No.
So that means when you write programs and you access memory using the wrong width, there's no warning from the tool itself. There's no automatic casting either. So that means you have to be very careful when you perform a move operation, so that you make sure that whatever you're moving has the same width as the intended destination.
Okay, so with the original component, we have the L1 register, the code 8049089, which have a compound.
That is determined by the linker and also determined by the loader of the operating system. In other words, that's not up to you to control.
And will it be different every time?
It can change every time. In other words, you cannot count on that number being the same all the time.
So what are we doing for it?
It is just a memory location. It is a memory location. That's all that you need to know. And you should refer to it as L1 and not that exact number.
Well, when you run the loader code, Greg, like it splits to that, whatever you've got, this is for all programming, into the memory somewhere. Right? It just allocates the space.
Correct.
So that's just an allocated number. It's
It
random.
is just a number that the operating system says, okay, I think this will be a good place to park your programs. Now, with Linux, with a particular kernel and a particular, with a particular kernel, it tends to load the program to exactly the same place. But if you switch the kernel, it may not load it to the same place anymore. And nobody says that the loader cannot just randomly pick a location to load the program. So that's why you cannot make any assumption that L1 is always going to be 8049089 hexadecimal. It is just that for this particular time that I run this program, it chose that location. Is that okay? Yep.
Why it shows us 47? Because you are writing 2 bytes,
Right.
and it shows.
But I'm only displaying the 1 byte. It has to do with the X command that I run here. I use x/bx, so it's only displaying the content of 1 byte.
It should display lowest byte. Lowest byte is.
It chooses whatever is at that location.
So when we store it should be like 47, 0, 0.
The 0, 0 is at location L1 plus 1. It's at the location of L1 plus 1. Any other questions?
Yes.
Those are all pretty good questions.
Yeah.
So that's an allocation of memory. If you convert to hex value, you get the actual line address.
Yeah, well, the hex value is really just another representation of the same address. In other words, the address is nothing more than an integer, right? It expresses the number of bytes from location 0 to the location where I stored the 47, hexadecimal. So you can look at that value as a base 10 number. You can look at it as a base 16 number, which is what we are seeing right here. You can also look at it as a long 32-bit binary number. But what base you choose to use is only changing the representation, but it doesn't change the actual value that you're trying to represent. So we have to kind of separate the value that we want to represent from the representation itself. But, okay? And you had a question?
So now, whatever was in L1 plus anyway, information was just
Yes, whatever is L1, whatever is at L1 plus 1 is now overwritten to 0. But it was 0 to begin with because that's how the program is initialized when it first gets loaded. Okay. Let me give you another question then. If I use another command line prompt to run the same program again, okay, using another instance of GDB, what do you think would be the location of L1? Hmm? Well, let's take a look. Okay, so I'm going to keep this window open. So this program is already loaded. It is in execution at this point. And by the way, any program in execution is called a process in operating system concepts. So we'll go ahead and do this all over again. Go to cisp310 and use GDB again to run the same program called direct. All right. I'll put a breakpoint on line 6 just like before. Run the program. And I'm going to use the X command again to take a look at that location. x/bx &L1. And you can see that it's the same location. How is that possible? It's the same location, but this one has the initial value, not the value that we have changed already. So how is this working? Why is it like this? It is all done through the concept of virtual memory. Okay? It's all done with virtual memory. In other words, each program, or each process, I should say, okay, you have the concept of a program, but a program is nothing more than a binder of instructions. Okay, it is static, it is just describing, how to do something, but nobody is doing something when you're just looking at the binder. A process, on the other hand, is a program in execution. Okay, it is the same thing as a worker reading the binder and doing something. So in this case, we have two workers. Okay, we have two processes using the same binder, which is perfectly okay. But each person, when you are talking about the data segment, it is the same as a little notepad. Okay, so each worker has a little notepad corresponding to the data segment of that particular process. When you have two different processes, the data segment of these two processes have nothing to do with each other. They're completely independent. Are we doing okay so far with that concept? Now, what about the binder itself? What about the binder that contains all the instructions? It depends on the operating system. Some operating system can say, okay, if you need to refer to the instruction, look to the exact same binder for the instructions. other operating systems can say, I'll make a photocopy for you, I'll make another photocopy for you. So that part depends on the operating system. But when it comes to the data section, it is all independent. Are we doing okay so far with that particular concept?
So 04908 is a binder.
It is a page in the data binder. It is a page number in the data binder to say, oh, okay, that's the location with a bookmark called L1. In other words, if you look at this data binder here, okay, so it's a data binder, okay, and here's a little bookmark, and it says L1. In other words, L1 is just a bookmark saying that, oh, you want to click to this location? You can say it is location 8049089 in hexadecimal, or you can just say L1. Well, L1 is a whole lot easier, right? Yep.
So, but for different process IDs, the value is different of L1. So does,
They can potentially be different, but in this case, they are the same.
so if they are though, does the operating system just cache the other value until the program or the process needs to see it? Like if two processes are using the same bookmark and it's different, the values are different for each of the variables.
But they are running in different memory spaces. And that's why it's virtual, because by the time your process starts and it sees memory space, that memory space is what we call a logical memory space. It does not actually correspond to the physical location in the 16 gigabytes of RAM that you have. When you run out of memory space, what happens is the virtualization mechanism can pick some of the pages from memory onto your hard drive, because they said, okay, you haven't done anything with this program for a while. I don't think you need these 4 kilobytes of RAM right now, but I really need it to do something else. I need to use that piece of memory. So it will swap out the 4 kilobytes of your program, which you haven't really used for a while, and then it will load 4 kilobytes of code or data that the operating system needs to use, so that you can, that's how virtual memory works. Yep.
Why did it revert back the old value, S3 value?
Because it's independent.
It's a different segment.
Yeah, every time you assign a data segment to a worker, you reinitialize that data segment to the value that you want it to be as the initial value.
Can you show a data segment here?
The data segment?
It should be different.
And it's the same.
Same?
Yep, same. It's because in virtual memory, that portion is also virtualized. So when you look at the registers, they are completely identical. Okay. Yep.
My question is that, okay, so in this instance of direct,
Right.
L1's current value is 0x47. And the other one is 0xF3.
Is it what? F3?
Yeah.
Oh, the content.
The content. So-
yeah, because these two data segments are different. So one guy has already gone past the instructions to change the content of that page to F3, whereas the other guy is still holding the data segment from initialization. So that's why they're different. But we are looking at two entirely different data segments. Basically, it's like a notepad. So these two notepads have nothing to do with each other, except for the fact they were initialized from the same template.
So my question would be then, so the hard location of L1 is that hex number, but the data segment, the virtual memory that each process is dealing with is different.
Correct.
Okay.
If you look at the actual memory location in your physical RAM, they will be at different locations. But by the time it gets to your process, you can no longer keep track of the actual physical location in physical memory, because that's part of the job of an operating system. You run it in protected mode. Part of the job of a protected mode operating system is to make this pretense that each process has the entire memory space, when it really does not have the entire memory space.
So it's really just a revenue.
It is just relative to location 0, and for whatever reason the kernel decides to start with that location. which can be completely random, right? Okay. Are there any other questions about what we have just talked about? No questions? So how many processes can I run from exactly the same program at any particular time? As many as you have memory for and combined with virtual memory, okay, or swap space. If you allocate a, let's say 40 gigabyte, swap space, you can fit a lot of programs like these.
Page file.
Yeah, page file is the Windows term to refer to that, but swap space is a Linux term, right? All right. Well, that's kind of like a digression of the main topic here, but it's a good one. It's useful. All right. All right. So we know this program works. So what we'll do next is I'm going to copy direct.s to indirect.s. In other words, we'll try to find a way to do exactly the same thing, but without using the direct operand. Okay. So this time I'm going to replace this instruction. A pound sign at the beginning of a line means the rest of the line is comment. In other words, the assembler would not pay attention to the rest of this line. So this time I'm going to use a move L instruction, and I'm moving $L1 to a register. I just picked EAX here, but there's no restriction that I have to use EAX in this case. I could have easily used EBX, ECX, or EDX. I just chose one of the four, which is EAX here. And this instruction now, move B, I'm using move B just to match the width of the memory location. So this time I'm going to move the same constant, which is 0x47, to the location pointed to by EAX. So this time I'm using a different addressing mode. I'm not using the direct addressing mode anymore. Can anyone kind of guess the name of this particular addressing mode?
Indirect.
Indirect. Well, the file name kind of gave that away, right? All right. But it's going to do exactly the same thing. Okay, these two instructions will do what that one single instruction did in the previous program. So let me just kind of quickly go through what each instruction is going to do. The first instruction is going to copy the value, okay, the value of L1 to register EAX. L1 by itself is nothing more than an integer. Okay, it's an integer value that is determined by the time we run the program. It's going to copy that value, which is 0, 80 something something 89 to register EAX. The second instruction is going to, okay, if you want to look at the second instruction from the C perspective, it's kind of doing this. It's looking at the value of the register EAX as a char pointer. It would do a dereference in order to store the value of 47 in hexadecimal. So it's kind of like, if you want to look at it from the C perspective, this is one way to look at it. Are we still doing okay so far? Okay. So let's go ahead and run this program, and then we can single step through these two instructions, look at the values of the register EAX, and then we look at the location that it is supposed to change, and make sure that it works the way it is intended. So assemble g-stabs-o indirect.o indirect.s link output to indirect from indirect.o gdb indirect. All right. So we list our program. We put a breakpoint on line 7, and then we run the program. This is right before we execute the instruction on line 7. Let's take a look at EAX first, which has a value of 0. This is before we actually change the content of the register EAX. We single step, we take a look at EAX again, and sure enough, it is now updated. And you can see that this instruction, this value is different from last time. It's no longer 8049089, it is 088 this time. So that means there's no guarantee, okay? Because the way I allocated memory from the data segment has not changed, okay? But there's no guarantee that it would use the same location again and again. And if you ask me, I think I have a wild guess of why it is 88 this time and not 89. It has to do with the single instruction that we used last time is 1 byte longer than the two instructions that we used in this particular case. But it's just my guess, we can verify that, but it doesn't really matter in this case.
We should verify it.
We should verify it. There's a way to verify. You can use obj dump, object dump, as a program to look at how the program is organizing its various components in memory. All right, so we'll go ahead and single step the second instruction. So after we single step the second instruction, the memory location at L1 should also change, in this case to 47 in hexadecimal. So we'll do x/bx ampersand L1. You know what? There's another way to do this now. Okay, we'll do this first. In case 47 is good, but we can do this in a different way. Because what we can do is to substitute ampersand L1, which is the address, with $EAX. Because $EAX refers to the current value in register EAX. And guess what it is? It's the same thing as the label L1. Are we doing okay so far? Well, let's go ahead and run this command first, just to verify that that really is the case. What if I do a print $EAX? It will just print the current value in EAX, which is a huge number. This is the decimal version of this number. I can always print it in hexadecimal, and that's the hexadecimal representation of the value in EAX at this point. So are there any questions about this particular GDB session? The commands themselves, what they're illustrating, why memory locations are containing the content that they are containing? Any questions? Any questions? All right, yeah. Yep, go ahead.
Why is this still 134, 5, 1, 6, 6, 7, 2? Why is it,
That's the value of EAX itself. If I do an IREAX, it would print the same value. One is in hexadecimal, the other one is decimal. That is, well, okay, that's a good question. Let me answer his question and then I'll come back to your question. Okay, that's a really good one. Yep.
What it says $EAX, and one time we got value, second time we got address.
Did you ask that question again?
Here it says $EAX, and one time we got value, another time we got address.
What's the dollar sign?
Say again.
What is the dollar sign?
What is the dollar sign?
Yeah.
The dollar sign is what we need in GDB to refer to quote-unquote.
No, in
variables.
assembler.
In assembler?
Yeah. And that line.
Okay, the meaning of a dollar sign is different depending on whether you're in GDB or in your source code. In the source code, a dollar sign precedes an immediate operand, but in GDB, a dollar sign precedes anything that is an internal variable in GDB itself. So the value of a register is quote-unquote considered an internal variable of GDB. So that's why we need to use a dollar sign to designate. Oh, we want to refer to a quote-unquote variable, but it's internal to GDB in this case. Yeah.
Why does x/bx give us value and print just the address?
That's the difference, because X is examine. Its job is to examine memory locations. So you have to give it an address to examine. Is that okay? Print, on the other hand, prints the value of an expression. It can be any expression. You can say print 5, and it will just print 5. But if you do an x/bx5, it will try to go to location 5 and print the content at location 5. In other words, when you use the X command, there's an implicit dereference to it already. When you use print, there's no implicit dereference. You can, if you want to, add the dereference, when you specify the expression to print, but it is not implicit. X has an implicit dereference. Yep.
So 47 is stored at memory location decimal 134 million. That was my question.
That is correct. Now let me run two more comments over, and then that will kind of really help to illustrate what print does, and what is an address and what is the content at the address.
So then could you then designate source code to move what's in the address of that decimal number to another location, and it would then move 47 without referring to 47, just referring to the address location? Like similar to how C you would move a pointer, kind of like a pointer to it. Could you do that where you would refer and say take the content of location?
Yes, we can use a direct we can take any operand as the first operand. Okay, so the first operand can be an immediate operand, but it can also be a memory operand.
Okay.
So you can copy from a memory location or the content of a memory location to a register. But you cannot do a memory to memory operand combination. That does not work. That's an artificial limitation, because it has to do with the memory cycle can only contain one extra memory access. So when your destination and your source are both memory operands, then that will require two accesses to memory, and the pathways just doesn't work out in that case.
So you couldn't say, copy into this memory location what's in this memory location.
That is not in one single instruction. So what you need to do in that case is to use a register as the quote-unquote temporary place to store that value. Okay, so what I'll do is I'm going to finish this discussion. Yep, go ahead.
So if you put in print /x ampersand $EAX, then it would print 47 in hexadecimal.
Okay, that's a question that I'm about to answer. So if I do not illustrate what you want to see, ask that question again. Okay. So the first thing I'll do is I'm going to use print here. So I'm only going to use print, for the following commands. So I'm going to repeat this command. This number here. Okay. What do you think is going to be the output of this print command? It's just that number, right? Okay. Nothing mysterious here. Okay. Well, I'm convinced. Now, the next thing I'm going to do is to say, oh, by the way, let's cast this to a char pointer. The parentheses are extra. They are not really needed because it's just one number. And it's going to print that. Okay? Well, what it's doing? Well, it's actually what it's doing is the number of $4 part of the hexadecimal 8049099 is actually the same thing. It is just the same number printed in hexadecimal. But because I cast it to a char, GDB is now getting smart and say, oh, this is a char pointer. Let me tell you what is at that address as a character. And guess what is the ASCII code of uppercase G? 47 in hexadecimal. Because 40 starts the, I think 41 is uppercase A. So you have A, B, C, D, E, F, G. Okay, so G is 47. Okay? Now, what if I add a dereference to this whole thing? In other words, I don't want to know the location itself. I just want to know what is at that location, right? And it would just say G, or 71 in decimal in this case. So is this helping to illustrate what exactly is L1 and what is the content at L1? Because those are the concepts that we need to get clear early on in this stuff.
So when you cast it like the number at the char, is it trying to return whatever's at that address as a character?
Yes. Okay. Now, are you talking about $4 or $5?
Both.
Both. Okay, they're different because $4. The main purpose of $4 is really just to give me the address itself. Okay, but it's an address of a char now because I casted it to a char.
That was my question.
But $5 says I don't even care about the actual address. I want to know the content at the address. So $5 does not even tell me the address. It just tells me the content at that location.
And my question was, is the reason why $4 is showing you the content as a char?
That's just GDB thinking I'm just going to do a favor.
So it's just it's not really implicit at all.
Yeah, it's just GDB doing me a favor in that case. Yep. What do you want? 71 is 4 7 in hexadecimal. 4 times 16 plus 7 is 71. 4 times 16 is 14 in hexadecimal, plus 7 is 64 plus 7 is 71. Okay, here's another, go ahead.
So, if you were to dereference $EAX, it would just print the same thing as 4, except without the G.
Yep. In fact, I can do this too. I mean, I can do something like this. I can say, is EAX the same as this number 1 3 4 5 1 6 8 7 2? Okay. Okay. Are we ready? Okay. So let's take a look at this expression here. Okay. It is using the equal symbol, which means I'm just performing a comparison. Okay. I'm comparing the value inside EAX to the constant that I just spelled out here, which turns out to be the address, right? Which is L1. So what do you think is going to be the output of this particular command? What is $6?
True.
Well, all I can say is going to be non-zero, okay? Because that's C and C++ says, anything that is non-zero is true. 1 is true, 2 is true, 32,000 is true.
-1.
-1 is true. Yep, exactly. So the only thing that can be guaranteed is it is non-zero. Okay? Whether it is really just 1 or not is entirely up to the implementation. So keep that in mind in your C++ classes.
In Visual Basic, -1 is true.
Because it's 1, 1, 1, 1, 1, 1, 1. The entire thing is filled with ones. Okay. All right. So is that helping to illustrate the concept? What is the register EAX itself? Okay. So that was an earlier question. I think you asked the question of, is EAX storing the address, right? I think that was kind of the nature of the question. Right? Okay. The answer is we don't know. Okay. The answer is we don't know. Okay. Let me answer. There was a hand over there. Yeah, go ahead.
Was it comparing confidence or just a guess?
It's comparing the value of registered EAX. The EAX is not a memory address, or a register is not in memory. So that's why we cannot refer to the address of the register. When we refer to the register, it's always the content or the value of the register. Okay. And I kind of lost my train of thought. Fortunately, it's all getting recorded, which means I can rewind myself if I want to. And I'm trying to remember what I was about to say. Oh, that's it. Okay, what exactly is in EAX? That was the question. Okay, let's take a look. What EAX is nothing more and nothing less than this. It is a 32-bit number. It's a 32-bit value, or a value represented using 32 binary digits. If you want to, if the instruction wants to, you can look at it as just 32 bits, nothing more and nothing less. But when you use that register inside a indirect operand, then you're treating that as an address. Is that okay? So this is a big deviation from the way we think about things in C and C++ or anything that is high level. In C and C++, when you look at variable x, the first question people will ask is, okay, well, it depends. What is the type of variable x, right? Is it an integer? Is it a char? Is it a string? And so on. But in this case, EAX has no type whatsoever associated with it. By itself, it is not a pointer. By itself, it is not an integer. By itself, it is not an unsigned int. By itself, it is not a float. It is just 32 binary digits. Nothing more, nothing less. The only time it has quote-unquote a meaning is when you use it in an instruction. When you say move L, %EAX, comma, something else, then you're copying those 32 bits to a destination, just the number itself. When you say move L in parentheses %EAX, then you're treating the value in EAX as an address. You go to that location, retrieve whatever 1, 2, or 4 bytes from that location, and copy that to the destination. So that was actually a very good question that you asked earlier, which is basically what is in EAX? Is it an address? Is it an integer? Is it 4 individual bytes? Can I look at that as 4 individual bytes, or 4 characters? Absolutely. It depends on the application. Okay? So now you have to remember, in this class, you do not think about a register or a memory location in terms of its type, because nothing has types in assembly language program. GDB tries to artificially add default types to stuff, which is actually making things a little bit more confusing than it has to. But when you're programming in assembly, nothing has any type. All you're doing is dealing with, bits, binary digits. Yep.
Okay, if you print AX, we'll give you 9088, and if you print AL, we'll give you 88, and AH will give you 900.
That is correct. In fact, let's make sure that is the case. So if I print, AX, it will be, well, since this is in binary, so it will pick the least significant 16-bit. So it will print, are those 16-bit already?
One more.
One more, like that. So if I run this command, it will print this portion. Okay, so let's double check. Sure enough, right? What if I print AL? It would just be 1000, 1000 in binary. Because what AL, AH, and AX are doing, they're just windows into the same 32-bit that we call the entire thing to be AX. Any other questions? Yep. /T is binary. Yep. If you want to find out all the code, help X will do it, because you can see in print in X, O is for octal, X is for hexadecimal, D is for decimal signed, U for decimal unsigned, T for binary, F for float, A for address, and so on. So we are running out of time today. I'm hoping that this class, or particularly these sessions that we ran through GDB, is useful, in your understanding of the concept of this class. All right. So don't forget, on Thursday, your homework assignment is due. On that day, I'll give you the second homework assignment. That has the same nature as the Find It one. It's going to be Find It 2, which will use all kinds of funky addressing mode, and you will have to find the big pattern in many words. That's the thing that kind of stuff that you have to work a little harder in that case.